Welcome. So today we want to look on higher order polynomials. Higher order polynomials. And we see that a polynomial is always presented in the form. Yes, so this is the general representation of a polynomial. So, and we see that n is the order of the polynomial. N is the order of the polynomial. And so we had said when n is greater than 2, that is 3 and above, then the polynomial is classified to be a higher order polynomial. And we say that a cubic equation is in the class of higher order polynomials. So before we proceed to learn on solving higher order polynomials, then let us first learn on 3 fundamental theorems that will help us. We are going to learn on these 3 fundamental theorems. We have the rational roots theorem, the remainder theorem, and the factor theorem. So these are the theorems that will help us when we will be solving the higher order polynomials. So let us start with the rational roots theorem. The rational roots theorem, it states that if p over q in the lowest term is the rational root of a polynomial fx equals to 0 with integral coefficients, and that q is not equal to 0, where our polynomial is fx represented in this form, then p is the integral factor of a0 and q is the integral factor of an. So the conditions for this theorem to be applied, first of all, it is talking of a rational root. Then you should have an understanding of what is a rational root or what is a rational number. Then the function or the polynomial equation should have integral coefficients. Integral coefficients means integers. So you should have an integral coefficients, and that q is not 0. Then in that case, p will be the integral factor of a0 and q will be the integral factor of an. So let us illustrate this using an example. So let us have this example. Fx is given as 6x cubed minus 37x squared plus 32x plus 15. First of all, this function, it has integral coefficients. So therefore, there is a possibility that it has a rational root. So we want to find the set of this rational root. This rational root will be a member of the set of the division of the factors of b and the factors of q. So therefore, the number p shall be a member of the set of all the integral factors of a0, and q is a member of the set of all the integral factors of an. So therefore, our rational root in the form p over q will also be, so finding the ratio of pq, we have all these values. So according to the rational roots theorem, provided that our polynomial consists of integral factors or the integral coefficients, then if this polynomial has a rational root, then at least one of these rational roots lies in this set of values. So therefore, that is the rational roots theorem. We should hold on as we look on other theorems for clear understanding. So let us turn to the theorem number 2. That is the remainder theorem. And the remainder theorem states that if the polynomial fx is divided by x minus c, then the remainder is fc, meaning it will be the function of c. This one will call you to remember the process of Rome or synthetic division of polynomials, such that we represent this as presented in this form. So let us work out using an example. We shall use just our original example to illustrate the remainder theorem. So let us say we want to find f2. Then we want now to divide the polynomial function by x minus 2. So we want to carry out this long division. this polynomial divided by x minus 2. So checking on the coefficient of x. So for it to be x, 6x cubed, then multiplied by x, 6 squared. So it will become, so we have this. So if we subtract, we will have minus 25 x squared. This is what we have. So then for us to have this coefficient equal to this, we multiply minus 25 x. So if we multiply times x minus 2, we have negative 25 x squared plus 50x. So if we subtract again, we have negative 22x plus 15. So for us, for these coefficients to be equal, we again multiply minus 22. So we have minus 22x plus 44. We will have minus 29. So this one, in this form, this is our remainder r. And in this one, this is our equation qx. So according to the remainder theorem, it means that our r, the remainder, is the function of f2. So we want to prove this. If we substitute 2 in our equation, we will have, so if we substitute 2 in the equation, we have minus 21. And truly, if you look at this, we have minus 21. So this one should be minus 21. There's a mistake. So this is the proof of the remainder theorem. Whenever we divide by the factor this, whatever we get is the function of this number. Yeah, so that is the remainder theorem. We are now to move on to the third theorem, which is the factor theorem. The third theorem is the factor theorem, which is just similar to the remainder theorem, but which states that if the function fx is divided by x minus c and the remainder is 0, then x minus c is the factor of the polynomial and c is its root. This is similar to the remainder theorem, but here it defines that if the remainder is 0, then in that case x minus c is the factor of the polynomial and c is its root. Yeah. So in an polynomial equation, what we are majorly looking for is the factor and the root of that polynomial. So straight away I want us to go and illustrate an example of a polynomial. So we want to solve it by applying these theorems that we have learned. So we want to solve this cubic function, or we want to find its roots. So according to the rational root theorem, this polynomial has integral coefficients. So that is the first thing. So it means that it has at least one rational root. So we want to find the set of these rational roots. B consists of the factors of a0 and q consists of the integral factors of a. So finding the ratio of b over q, we shall have, so because our polynomial function has at least one rational root, then that root must come from among these factors. That root is the member of this set. So by substituting every factor of in this set in the polynomial we have. So by substituting all the values in this set, we found that if we substitute 2 in our equation, we find 0. So therefore, we have found that 2 is one of our rational roots. So therefore, we proceed to long division to find the function qx. So let us carry out this long division. So we take 2 will be so by long division we have found out that our function qx is 2x squared minus 7x plus 4, which is a quadratic equation, and our remainder is 0. So this one proves the remainder theorem or the factor theorem. that because 2 was the root of the polynomial, when we divided the polynomial by this factor, x minus 2, then our remainder was 0. So therefore, we represent it now as, this is how we will represent the polynomial, such that our first root is 2. By solving this quadratic equation using the quadratic formula, we found out that x2 will be 0.719, and so we will now present our polynomial as, this is how we could represent our polynomial. These are the factors, and these ones are the roots. Yeah, that is how we can solve a polynomial. So let us now look at another example of a fourth order polynomial. We want to solve now this fourth order polynomial presented as this. So we need to find the value of p, the values of q, the values of the ratio p over q. So b consists of the factors of our a naught, and q are the integral factors of our a n. So the ratio p over q shall consist of the factors. The ratio p over q shall consist of the integral factors of those values. So therefore, at least one rational root of this polynomial falls in these values. So by substituting, we found out that if we substitute, value of 1 gives you 0, and also 2 gives you 0. So therefore, 1 will be our first root, and 2 will be our second root, such that x minus 1 shall be our first factor, and x minus 2 shall be our second factor. So by long division, we are going to find the remaining factors. Our polynomial shall be presented as x1 times x minus 2 times qx. So by long division, we are to find the function qx. So we have take 4 x cubed will be 4. So we have that one. Then now we multiply 15 x squared. Now then we will have, then we multiply positive 9 x, we have, then we multiply, then we have 10x. Our remainder now will be 0. And now we will take out this equation and again divide it by the factor x minus 2. So we multiply, then we multiply plus 7x, and so we have, so we multiply, we have minus 5x, and the remainder is 0. So finally, this is the equation qx. And so now we are going to present our polynomial as, where now this one is a quadratic equation. By solving this quadratic equation using the quadratic formula, we have, so our that root will be negative 0.545, therefore the root will be 2.295. So we will now present our polynomial as, this now will be the factors of our polynomial. So by this, we will be able to solve all the higher order polynomials by just using the method of long division. Then by applying the rational root theorem, you can be able to solve any polynomial of any order. Thank you.